So in this video, we are going to study we are going to study the capacity of a channel in both the transmitter and the receiver side has the channel side information. However, in this video, in this in this problem, we are not going to maximize our capacity so that we can transmit the maximum number of bits into the channel. But the objective in this case would be to maintain a constant signal to noise ratio. Remember, we would still assume that both the transmitter and the receiver have the channel side information. So this transmission strategy is called channel inversion. So in channel inversion, what happens is, remember, both the transmitter and the receiver side have the channel side information, so you can adapt your power at the transmitter end. So in the last couple of videos, we defined our instantaneous signal to noise ratio gamma j to be equals to the transmitted signal power in the jth state times the gain of the channel at the time of the jth state divided by the noise power n naught b. That was your jth state signal to noise ratio. And then we defined another variable gamma, and we said that let gamma is equals to p bar gj over n naught b. So it is related to the jth state of the channel, but when a constant power p bar is transmitted into the channel. And then because of the help of this new variable gamma, we said that we can define this gamma j in terms of this gamma. That would be equals to pj gamma over p bar. So pj is the share of the power that is transmitted into the channel when the channel is in the state j. So in this way, we have defined our signal to noise ratio. And in the channel inversion, we want this signal to noise ratio to be constant regardless of what state you are in. So let's say we want this to be a constant sigma. So in this case, what would happen that your power allocation strategy, Pj over P bar, would be equals to simply sigma over gamma. And because of this fact, because this gamma is appearing in the denominator, we said that we are going to invert the channel at the transmitter side. So that is what you're going to do. So you would determine what is your channel, instantaneous signal to noise ratio, and you would simply invert it before the transmission. But what happens with the capacity? So remember, we said that we have to adhere to a constant average, total average power constraint. That means that integral from 0 to infinity, P of gamma, P gamma of gamma, d gamma must be less than or equals to P bar. And even if we take this as in an equality constraint, that would mean that integral from 0 to infinity, P of gamma over P bar, P gamma of gamma, d gamma must be equals to 1. In the discrete time, this would be equals to summation j, pj tilde. So the discrete time, the equivalent discrete time would be summation j equals 1 to n, pj tilde must be equals to 1, where pj tilde is the probability that the channel is in the state j. So hence, if you have this is pj over p bar times pj tilde must be equals to 1. So now pj over p bar is nothing but sigma over gamma. So now you can replace p of gamma over p bar with sigma over gamma, and that would mean that in this power allocation strategy, because of this average total power constraint, you would plug in sigma over gamma, P gamma of gamma D gamma is equals to 1. In other words, this sigma is a constant. You can take it out. Sigma times integral 0 to infinity 1 over gamma P gamma of gamma D gamma is equals to 1. This quantity that you can see is nothing but the expected value of 1 over gamma. So this quantity is nothing but expected value of 1 over gamma. And hence you can compute what is sigma. So sigma is nothing but 1 over expected value of 1 over gamma. So you have computed sigma in terms of a function of a gamma, and now you can compute what is the capacity. Because your signal to noise ratio is constant, your capacity is simply B log base 2 of 1 plus your signal to noise ratio, which is sigma. And that would be equals to B log base 2 of 1 plus 1 over expected value of 1 over gamma. So this is your channel inversion strategy. This capacity may take a big hit under severe fading. In fact, if the channel is undergoing Rayleigh fading, the capacity under channel inversion would be really small or very close to 0. So in order to circumvent this problem, people have devised another strategy, which is called truncated channel inversion. So in the truncated channel inversion, your power allocation strategy P of gamma over P bar is equals to sigma over gamma, which is your channel inversion, but only when gamma is greater than or equals to some threshold gamma naught. And if not, you allocate nothing. So if your channel, your instantaneous signal to noise ratio is less than a threshold, you would not transmit anything. Right? So it's analogous to the outage, the capacity with outage which we studied in the case of RX CSI. So this is in this case, the transmitter has the power to allocate different powers, and the transmitter would stop transmitting anything when the signal to noise ratio is less than a threshold. And in this case, your capacity, your sigma would be almost the same, but it would be slightly different. It would be 1 over expected value of 1 over gamma, but you put a small gamma naught here. That means is that in order to compute your sigma, you would do what? You would not integrate from 0 to infinity. Rather, you would integrate from gamma naught to infinity. What? 1 over gamma P gamma of gamma D gamma. So that would give you your sigma. And as you are not integrating from 0 to infinity, so you would have slightly better signal to noise ratio on average. And then the capacity would, with some outage, we can call it C out, would be equals to B log base 2 of 1 plus 1 over expected value of gamma, but you put a small gamma naught here, but that must be multiplied with the probability that gamma is greater than or equals to gamma naught. In other words, you need to multiply with the probability of non-outage, right? And then what gamma naught you must take, and that becomes an optimization problem. So this is your capacity with outage when your acceptable signal to noise ratio is gamma naught. But what gamma naught would give you the maximum maximum capacity. That is an optimization problem itself. So your maximum outage capacity, you call it C, that would be equals to, you would maximize over gamma naught B log base 2 of 1 plus 1 over expected value of 1 over gamma. But there's a gamma naught here, so that you integrate from gamma naught to infinity times the probability of non-outage. So that would give you the total probability. Under this suboptimal regime, where you would start transmitting whenever your gamma is greater than gamma naught, and the gamma naught that maximizes the capacity should be your design parameter. So we would stop here, and we would do the capacity comparison in the live session today. I will stop recording.